Okay, so welcome back, everyone. We're all refreshed by tea. Oh, we have to wait for the signal. Exciting the electrons in our material, and then these waves are coming out and they're turning out to be plane waves out here, and we have an equation we have a mathematical expression for this wave, and the mathematical expression looks like this exponential, which is just a sum of sines and cosines. So it's just a beautiful oscillating in space and in time, and we have an amplitude, and the amplitude is telling us how strong the scattering signal was from the initial condition, and it's proportional to the electron density. So the prefactor of this exponential is actually an electron density. And now if we have more than one atom here, we can have two scattering events that take place from atoms that are separated from each other. And what we'll get is we'll get interference. So instead of getting a single plane wave out here, we'll get an interference pattern, which looks like something like a Young's two-slit experiment, for example. Now, what we ran into is that this is the amplitude. It's proportional to the electron density. But what we actually measure is the intensity, not the amplitude. And the intensity is the mod squared of the amplitude. So this is the quantity that we measure, and in a PDF experiment, it's this guy here. We say I elastic because there are some other scattering processes which don't convey structural information. There's Compton scattering, and there's other contributions. So this is sometimes called the elastic scattering, or sometimes the coherent scattering. So this coherent scattering intensity is just this intensity that we measure in the detector, and it's a function of this momentum transfer Q. So this is what we measure. You have your diffractometer data, and you saved it as a text scattering factor of zinc squared, plus the concentration of oxygen times the scattering factor of oxygen squared. So when you're using PDF getX3, and in the config file you have to write down the composition, you're basically telling it how to compute this guy. And then we basically divide also by something that's similar to that, but there's one key difference. This one is CI-FI squared, but this one is CI-FI over I all squared. So in this one, in terms of kind of statistical mechanics scattering, so we don't need to worry about that. So single crystal, okay. If you're going to do structure solution, the approach is you have your crystal, you get dots on your detector, and then you do structure solution. And it's really powerful. We can actually solve structures that look like this now. Not me, but people. You don't have a single crystal like this. You actually do a powder diffraction measurement. And so a powder diffraction, this is what a single crystal experiment looks like. You've got a crystal, it has a certain orientation, you have an incoming beam, and you'll get a single spot from it. Positions to collect all of the diffraction spots, and it measures the intensity of them all, and then you can run those intensities through the structure solution problem, the program. So what if your sample is made of two crystals and they satisfy the Bragg condition? Then you'll get actually two spots. One spot will come from this crystal and one spot will come from that. We're always scattering at some fixed 2 theta, so that's a Bragg peak. But whereas you might be working in the horizontal plane because your detector is rotating this way, or it might be in the vertical plane if your detector's. So the question is, powder diffraction, every crystallite contributes to the intensity in by sharing. Is that true or false? And actually the answer is that only a tiny minority of grains in your sample contribute to the scattering. They have to be exactly at the orientation for the Bragg relation to hold. So basically, I don't know what the percentage is, but it's maybe 90% of the crystallites don't diffract at all, and all of your signal is coming from like 10% of them. Cell through to get base, and you can pull up different compounds which compare well with your pattern. So now to do this kind of task, this is a very good kind of task for machine learning. So that tells you, roughly speaking, what structural class your material has, but that's when you do the refinement part. So your material, it may have defects, and it may be doped, it may have a slightly different composition from the one in the database. It may be nano-sized, which we're very interested in. There's also thermal vibrations, that's not in the database. And that's where the refinement comes in. So then we do a refinement process. Refinement means that we've got a structural model we got from the database, but we vary the parameters a little bit in order to get a good fit. So that's what we were doing in PDF GUI. In PDF GUI, we were doing the refinement of the structural model compared to the PDF data. If you do the refinement of the model compared to regular powder diffraction data, then you're doing Rietveld refinement. So this is the same thing we did: collect the data, find the phase, suggest a structural model to the program, calculate the diffraction pattern, compare the experimental data, change the structural parameters, iterate again and again and again until you have a good fit, and then PDF GUI or your Rietveld program gives you all the good results, and you publish the paper and become rich and have a life of luxury. Okay, so when you do a Rietveld refinement, and it's not Rietveld but as is PDF, but you get something that looks like this, and the black curve is measured, the red curve is calculated. This blue curve is the difference between the measured and the calculated. It's very flat, that means it's a good fit. And then these green dashes here tell you everywhere where there should be a Bragg peak. And that's very helpful, because if you see a peak in some place where there's no tick mark, it means you've got an impurity and your phase is not phase pure. Okay, now let's say that we have, so peak position gives the unit cell, peak intensity gives the unit cell content. The peak broadening tells you about particle size and nanostructure. So broader and broader. So it's kind of illustrated here. This is a diffraction pattern from bulk gold, and these Bragg peaks are extremely sharp. Now we have 100 nanometer particle, so this is on the same scale, 400,000. So you see that the intensity came down for 100 nanometer particle, but the peaks are still pretty sharp. 60 nanometers, it's coming down, and now you can start to really sense that there's some little bit of broadening. 50, 40, 30. So now we're down to 20 nanometers, and these peaks are starting to get broad, and the intensity has come way down. Actually, the integrated intensity hasn't changed. It's only the peak height that's changed, and the peak height has come down because the peaks have broadened. 10. So you still get actually a fairly good diffraction diffraction pattern with 10 nanometer nanoparticles, and that's really small. But so if you have anything down to 10 nanometers, you can do a lot. And the intensity looks like this, and really there are no Bragg peaks left at this point. But we still have diffuse background that the PDF will give us. I'm going to take a break from this right now because actually some people wanted me to show how you do temperature-dependent refinement in PDF GUI. So we're going to switch now. So this is PDF GUI, and oh, I have it here, I think. No, okay, I'll just start here. Okay. All right, so I've got a new PDF. There's this file here which is temperature dependence of nickel, and here I have many data. So now I'm going to the QDAMP, QBroad. So I'll just leave those, and I'm going to do the ADPs, which are the thermal factors. Okay. So this I want to be at 3. Let's do at 3. So my thing has got 3. Add. And what I do is I select these guys, all of them, and I open them up like that. Now something that we've done is that we've been very clever. So this is very nice. So we go OK. And now if we look at this fit pane over here, we have many fits in here, and so we can actually run them all sequentially. And so I think so what we do is we click on this fit, and if you do Control-Shift-A, okay, so I'll write it here. So Control A for all. It's going to be fitting them all. Oops. Control-Shift-A to select all the fits. Now if I go down to my plot control window down here, I can choose different things on my x-axis and different things on my... But actually as I get to higher and higher temperatures, the agreement gets worse. So I might want to go and investigate that. Normally I like my agreement factors to stay constant. I also see that there's some problems here, so that I may need to actually not proper convergence, that those fits didn't converge properly, so I should go back and the amplitude of thermal motion. So they were 3, I think. Yeah, so they're increasing too. So we've just extracted, we've now measured the thermal expansion of nickel, and we've measured the increase in the amplitude of thermal motion of nickel. But anything that you've refined you can plot in this way, like atomic positions and things. We don't have a macro for that. You could kind of fake it though. What you could do is you could save your file name and you could give the macro like that. In your notebook, it's a good idea. You would save it, and that would give you an image file, like a .png file that's exactly this. And you can do all the usual things in, you can zoom up and down, and you can... Actually, this was the thermal parameter, and what you see is actually it's fairly linear in high temperature region, but it curls over in the low temperature region. This is very characteristic. And actually thermal factor down here, it would actually go up there. But this thing is deviating upwards from that. And the probable reason for that is actually anharmonicity from your data if you're careful. And you can actually extract the Debye temperature, which is telling you how stiff the bonding is in your material, by fitting to this straight line region here. Actually, you can fit over the whole range, but that's a lot of work, but I can immediately tell you that this material has a very low Debye temperature, because it's actually almost linear down to 80 Kelvin. So the way that the Debye curve goes is like this. So this would be U ISO, so some kind of thermal parameter. This is temperature, and it's flat at low temperature, and then it curves up, and then it can stop moving. But because of quantum effects, it peels away from that linear behavior at some temperature, and then it comes in flat. And even at zero temperature, the atoms have some finite motion. It's not thermal motion at that temperature, it's quantum zero-point motion. If I look at my nickel, I'm already at 80 Kelvin, which is quite a low temperature. And it's beginning to curve over, but it's happening very slowly. So my estimate of what the Debye temperature for this would be, this is actually a fairly low Debye temperature material, but the Debye temperature is going to be where it's solidly in the linear regime. And so this one is in the linear regime kind of up here at 250. So the Debye temperature of nickel is probably somewhere in the vicinity of 250 Kelvin. Okay? So let me show you what the other macros are. Fits, macros. So I showed you temperature series. It's possible to also do a doping series. I think it works in the same way, and probably the letter that you use is X for the composition X. So it's probably some number times X, but read the manual. And the R series is a very important one that we use a lot. And again, I don't know how the R series one works, so read the manual. But what I wanted to show you now was a real sign. How many of you have heard of CMR? So older people in the room, such as myself and Shiva, are knowing what CMR is. So CMR stands for colossal magnetoresistance. What's magnetoresistance? So if you have a material and it's a metal, you can measure its resistance, its electrical conductivity or its electrical resistance. Magnetoresistance is that you apply a magnetic field to that material and the resistance changes. Now, magnetic field is usually a very benign, low energy phenomenon. Like most things, you put them in a magnetic field and they don't experience very strong force. Once was actually, and the group at IBM, they really wanted to find devices that had a large magnetoresistance. So why might you want to have a material with a large magnetoresistance? What could you use it for? And I move it to low magnetic field place, so I can have a magnetic field detector. And it turns out that magnetic field detectors is huge business.
You are playing with spins in this case?
It's always going to be playing with spins. Yeah, because it's actually spins. Yeah, so spins in the material are responding to the magnetic field, but they have to also couple to the electronic system. So you want to take advantage of this coupling of the spins to the electronic system, and that's usually very weak. So most materials have a very low, so you basically can't make a device that can detect this magnetic field out of a usual material. So you want a material which has a giant magnetoresistance. In other words, you make a small change in field and you get a big change in resistance. And what they were playing with at IBM and in France was with these spin tunnel junctions. So they would take a ferromagnetic material and an antiferromagnetic material, and it would pin the ferromagnetic material. And then you would pass a current through that. And it turned out that the resistance to the passage of current in that kind of device was very dependent on the magnetic field. And that earned actually Albert Fair your magnetized region has to move under the detector, and if there's a different bit which is set differently over here, it has to be far enough away from this guy that it doesn't overlap. So they wanted a static way of measuring it, so they could go to the address on the disk of this magnetized region and read it directly, and they could do that with this giant magnetoresistance. So it was like a huge deal. Some calcium manganese oxide, and they found that it had a magnetoresistance that was thousands of times higher than the giant magnetoresistance that Fair got his Nobel Prize for, and it was just so large they called it colossal. So giant is really big, colossal is extremely big. Metal, so it's a metal, but it has ferromagnetism. And then above it here, it's actually a paramagnetic insulator. So simply taking this material with this composition and warming it through this phase transition, you can turn it from a metal to an insulator. But the key thing was actually that the metal is ferromagnetic and the insulator is not ferromagnetic. So what you could do is you could sit at some temperature just above that line. And then you could apply a strong magnetic field. And the magnetic field will couple to the ferromagnetic state, but it won't couple to the non-ferromagnetic state. And so it energetically stabilizes the ferromagnetic state. So what it does is it pushes this phase transition line up in temperature. So if you simply sit just above that line and apply a magnetic field, you can actually turn the material from an insulator into a metal by the application of a magnetic field. So that's basically the origin of this colossal centimeter. So it's 10 orders of magnitude change in resistivity for the application of whatever that field was, 8 Tesla. Colossal magnetoresistance. We're all extremely excited. So this is the phase diagram here, and this is what I just described to you. That's the ferromagnetic metal paramagnetic. So that's this thing. Now, okay, that's really exciting that we can just measure it and we can understand this importance of magnetism. But what is it inside the material? What are the atoms doing that causes this effect to happen? So what we have to explain is we have to explain why it's a ferromagnetic metal at low temperature, and 1 times 3 plus, we've got 3 minus, and we've got something's wrong here. Oh, I guess this is 3 plus. Okay, yeah. So then the manganese is in the 3 plus state when it's pure lanthanum, but calcium is 2 plus. And so what's happening is I'm increasing the manganese charge towards 3.5 plus. Now, total number of electrons that I can share between the manganese, but I don't have enough for all of them. So what I do is I make some of the manganeses 3 plus, and when I run out of electrons, the remaining manganeses are going to be 4 plus. Okay. So there's basically 2 ways that I can distribute the electrons. One is where every manganese is 3.5, and the other is where I have a mixture of 3 plus and 4 plus. So the key insights was that if you have a 3 plus manganese, it actually is a GIAN-Teller, elongates this bond and shortens that. It's a GIAN-Teller distortion. Now, the 3.5 plus case, the metal case, it turns out that this guy gets quenched, it gets removed, and so everything looks like that. So what we did is we did PDF, material, metal. And so in some sense, the difference curve between those 2 data sets is my signal. That's telling me what's different between these 2 states. And it's the red curve down here. So it kind of looks a little bit noisy. But it's actually signal, it's not noise. Now what I did is I then took 2 models, and I was looking for this GIAN-Teller distortion. So one model is looking like this. It has a mixture of undistorted and yarn teller distorted octahedra, and I arranged them in space so that they filled space so that I could use PDF. The red curve is the difference between the two data sets. The green curve is the difference between the two models. And you can see that there's essentially astoundingly good agreement between the green and this basically confirmed in 1996 when we published this in PhysRev Letters. This basically confirmed that this was actually what was happening in these materials. It was the first really direct evidence. People had hypothesized this. This was the first direct evidence that it was happening. And this paper has 467 citations now. It's a very highly cited paper. So it's very important for understanding these CMR manganites, but it was also very important for PDF because before this date, a lot of people's scattering length for neutrons is a negative number. So we actually get a negative peak in the PDF, which is coming from manganese to oxygen. And if you have a regular octahedron, you're going to have 6 manganese to oxygen distances, but they're all going to be the same length. So you're going to get a single peak. And if you have a yarn teller distorted octahedron, you're going to get 2 manganese oxygen distances that are long, and you're going to get 4 that are short. So that manganese oxygen peak, in principle, will split into 2 peaks. So it's actually in the PDF, because the peaks in the PDF are telling you the interatomic distances. You can just directly look at the PDF and kind of tell if it's going on. So if we look at this undoped MNO6 octahedron, and you can see it directly in the data, you don't have to do any modeling. You just look at the PDF, you see it. What we did then is we went up in temperature, and it goes all the way up to 1,000 Kelvin, and actually the material goes into a rhombohedral phase, but crystallographically, in this phase here, crystallographically there's no yarn teller distortion. So this material would have yarn teller distortion down a bit overlapped, but there's still a short and a long bond. So crystallographically, there's no yarn teller distortion, but if you look in the PDF in the local structure, there is a distortion. So how do we reconcile that? So basically what's happening is that you have these yarn teller ions here, but they can take different orientations. So it can be this direction, or that direction. And actually, if it becomes dynamic, it can flip. So my long bond, that. So we can see the crossover actually in the PDF. So this is actually a fit to that data. So the low temperature data we have, this is coming from a PDF GUI fit now. And at low temperature we have this long bond and the 2 long bonds and 4 short bonds. Short and long bonds. Now this is a peak position versus temperature. Now I'm going to do this bond length, not bond length versus temperature, but bond to the R range that we're fitting. But we're becoming dominated by the high R structure. And the high R structure has no distortion, the low R structure does have a distortion. So if you then plot some bond length versus R max, we know that at low R, so in the low temperature phase, which is fully ordered, at low R we have 4 short and 2 long, and actually at medium R we have 4 short and 2 long, and at high R we have 4 short and 2 long. That's because this yarn teller distortion is crystallographically long range ordered. So the yarn teller distortions are all ordered. That's at low temperature. But at this higher temperature, what happens is at low R we have 2 long, 4 short, and at high R this distortion is starting to go away. And in this even higher temperature one here, we have this 2 long, 4 short, but then by 15 angstroms, it's actually gone down to undistorted. And what we can do is we can measure the range of R that you need to go to for this crossover to happen, and that's telling you the domain size in your material. It's telling you what you have is yarn teller distortions, and they short range order, but they're not long range ordered. And where this thing crosses over is the changing, but they're all still there. And actually we see a little bit of, we couldn't get close enough to the phase transition, but we can see critical behavior here where the this is the inverse correlation length, so it's actually going down to 0. If you plotted it directly, it would diverge, go up to infinity. So we're actually extracting the critical dynamics of the structural phase transition, if you know about structural phase transitions. Yeah. Okay, so that's what I wanted to say, that short-range ferromagnetic, ferroelectric distortion, but over long range you don't have it. But it turns out that it's we're seeing this kind of behavior in many, many different materials. So I'm going to stop now, but the basic idea is it looks like this, that you can have some domain which has a broken symmetry and another domain which has the same broken symmetry but a different orientation. And when you look at low R, you're looking inside this domain. We're finding that the short-range order is very important, that actually the short-range order is different from long-range order, and a lot of the material properties. Right at the beginning of the talk, we talked about carbon and how the arrangement of atoms determines the properties. And what we're finding is in many crystalline materials, the local structure is different for the PDF method, and it's quite boring, especially chapter. If you're serious about PDF, you're going to want to try and get at your institution a Moly K alpha tube source. But if you only have copper K alpha, if you measure data in a copper K alpha, you want data will give you a high resolution PDF, but you have to argue something like local structure is important. I think local structure is different in this material. My copper K alpha data can't tell me the difference. I think synchrotron data will help. If you can argue that well, then we'll say, okay, fine, send us a sample, we'll measure it, we'll send you the data. Okay, so those are a number of things that I wanted to say. And I hope that you'll, or at least some of you, will get excited and try it. So everyone in my group here, this is from actually not this year but last year, and this is actually Columbia campus. This is the alma mater statue. This is a Low Library, which is very famous. We actually like to work with groups well. And this is actually inside the experiment hall at NSLS2 at Brookhaven. And the ring is a kilometer long. And so they have these tricycles it's kind of like cycle rickshaw in the US. But when it's very late at night, like 3 or 4 in the morning, and the students are getting a bit antsy, they like to go and have like tricycle races around the ring. So if you were actually able to come and do an experiment, you could reach the pinnacle of your career and become a cycle rickshaw walla. Okay, so thanks.
The technique of PDF analysis is, and it is very essential for people working in nanomaterials and even in bulk materials. As I mentioned in the beginning of the course, Professor Simon Billingy is the best person, and you can well see how well he delivered the lectures and how he interacted with the students. And I thank him on behalf of all the participants. Thank you very much. Thank you for accepting our invitation. I remember I first contacted him in February, and he is very busy in his research work and also in his teaching work. The new academic session is going to start in September 5th. So immediately when he returns to US, he will be busy with his teaching, and we know that he is a remarkable teacher. Thank you very much.
My pleasure.
It's our great pleasure, and we really will miss you also. And I think the students, they will contact you if you have some research problem or if you have some questions. he is always available. So if there are any specific questions, brief or some concise questions, we can have a small session for about 5 or 10 minutes for any comments or any questions. Please feel free to ask.
How to deal with more than one there in my data?
Yeah, so if you have more than one, phase, you need to make two models. You need to create a fit, which is you need to make a fit which has two models and one data set. So the one example that we have for that is so new fit. Now if we go to, we're going to add data, new data set. So the one example that we have here is two-phase refinement nickel silicon. So you should, if you look inside here, we have, there's actually three data sets. One is pure nickel, one is pure silicon, and there is, okay, it's not there. So they want you to build your thing from scratch. Okay, so there's none there. Yeah, okay, so there's none in this particular example. You have to build your own, but let's say that we were doing one of these other ones, like this one. You might find a CIF file in there, and you would load the CIF file for one phase, and you would load the CIF file from the other phase. So we can just do that. I'm going to load the wrong phases, but it doesn't matter. So let's go to this guy. So I could load this CIF file. But what I would do is I would add a new phase to the same fit. And I would load this one. And I've got to find another one now. Okay. So now I've got a single fit. It has two structures, two models, one data set. Then the rest of the refinement is kind of the same.
You have to work and practice the essential training and exposure to the problems. So you have to now spend time working on the programs.
If you get into difficulty, what's the best thing that you should do? Yeah. Firstly go and read the DiffPy users Google group to see if your question is already answered. So let me just do that now so that you've got an example. You say, oh, I don't know how to do two-phase refinement, so I mean, actually, you should be able to figure out from the manual. So firstly, read the manual. If you can't get the answer from the manual, read this book that we gave. If you can't get the answer from that, then you want to go to the Google group. So actually, I don't have internet in here. But if what I always do, because I don't remember the link, is I just Google for DiffPy -users. So if you just Google for DiffPy-users, you'll get it. I have no internet, so I can't get there. And then you, that anyone's ever asked to see if there's one relevant to your problem. That's the first thing to do. And then if it's not answered in there, then post your own question. And then what will happen is a dialogue will happen. So it's a little bit like sending me an email asking me the question, except that now anyone in the community who knows the answer can answer it, It doesn't have to be me, and I'm usually too busy to answer. So you get an answer more quickly. And the second thing is that answer is saved in a way that everybody in the community can share that answer. So that's strongly encouraged.
If you spend time, you can find all answers yourself. You have to think or discuss with your colleagues, so you will learn things.
But don't be shy to post questions, because if everyone solves the problem on their own and they don't post the result, nobody else learns. So there's some balance. Some questions are written in the manual, and then it's just you're creating extra overhead for us to tell you to look in the manual. But if it's not in the manual, we want you to ask it, because it actually is. This Google group is becoming like a manual. And if you're having that problem, there's a good chance somebody else had that problem. So yeah, don't be shy. Post to DiffPy.
Thank you, Simon, once again. I may mention that all these lectures, they are permanently available on internet. You can go to YouTube and type Live Chandigarh. So you will find Professor Simon's lectures. Live Chandigarh.
Live Chandigarh.
Yeah, that's the name of the company which has recorded and put it on YouTube. So you have now all graduated. But before that, we have a test.
So then they haven't all graduated,
Yeah.
so they pass the test.
Yes. You have to pass a test. So you can please spread out, maybe 3 participants per bench or per row, and we distribute the questions. So I am distributing to you the one question paper. There is a blank sheet behind it, and I will give you an extra sheet also. So you can write your answers, brief answers, your name also. You can sit, you can take this. You can write your name on the question paper. We will give you some extra papers also. Blank sheet with it. Yeah. Please start. I'm distributing to you one feedback course evaluation form also. So you can write, you can give your suggestions or inputs. On the evaluation form, you don't have to write your name. It is optional. If you want to write, you can write. You can fill your sheets. मिली इसमें डालो डिवाइड कर दो
ठीक है जगह इतनी है टोटल। जो फोटोग्राफ भी है ना उसको अलग में डाल देना, एक फोल्डर बना लो, अभी 2 4 और भी खींच लो।